Here we're going to look at two related questions about what we see when we look from one material into the other with different index of refraction. So first let's look at the picture. It's not quite right, but it's close enough for us to see what's going on. So the idea here is that the light ray that's actually happening here is from the instructor down to the scuba diver. Looks like this. So the light comes, for example, from the instructor, and then when it hits the water-air interface, it bends towards the vertical. Okay, it bends towards the normal. So this would be, for example, our theta in the water, and this would be our theta in the air. Okay? But from the point of view of the instructor, of course, this light coming from the diver, which is along this line, is actually coming from his point of view along this line, right? So he sees the diver, the instructor sees the diver up here. That's where the instructor observes the diver. Directly overhead, and the diver sees the instructor actually not shifted over, but actually somewhere up here. Okay, it's just they did it, they sort of exaggerated it because they ran out of room, right? So we would actually, because this angle is actually exaggerated here, we would actually see the instructor sort of up here. Okay, if these angles were all to scale. And so that's what we're going to look at. And so I'll redraw this, but I think this picture is actually helpful. We'll just look at where it's useful and where it's not. But the main thing I want to focus on is this, this first piece, which is actually this highlighted ray that we're interested in, because that's really what the first question is asking. The first question says, looks at the scuba diver, what angle does the ray from the instructor's face make with the perpendicular? That would be what I've labeled theta air, where the ray enters. And the angle between the ray and the water is 25 degrees. So in this diagram, we have then theta water is equal to 25 degrees, and that's pretty much to scale. And the question is, what is theta air? Okay, so that's question 144. And that was pretty straightforward to figure out, because we just say N of water sine theta water equals N of air sine theta air. And the index of refraction of air, we're setting that equal to 1. That's close enough to the vacuum speed of light. And then this gets us, if we look it up, it's 1.33. And so if we put that in, we have 1.33 sine of 25 degrees is equal to 1 times sine of theta air. So when we calculate this out, we get theta air is equal to 34 degrees. So it's a bigger angle as we expect. And this is where you can start to see the drawing goes a little awry, because this angle looks more than 45 degrees. Okay, so as we set this up then, so that's the first part of this problem. So now we know that this angle is 34 degrees, and this one is 25 degrees. All right, so what we're now asked is to use sort of the diagrams that the diver is 2 meters below and the instructor is 2 meters over. The question is, find the location of the diver as seen by the instructor. That is, find this new height, right? This height right here. And also find the location of the instructor. Find the instructor's height. Okay, so we'll say height of instructor as seen by diver, and this is the depth of the diver as seen by the instructor. Okay, so I'm going to do both of those a little bit separately. You can keep this image in mind if you want. I'm going to redraw it. We'll look first at, so here's our water. We'll look at, and I'll try to draw the angles a little more to scale. So we're going to look at, here's the 25 degrees theta in the water from the diver. So the diver is down here looking up, and this angle kind of comes out like this, okay, so it's not such a big variation, of 34 degrees, and the question really becomes then, where is this instructor located height-wise, if he's still, of course, 2 meters away, which is this diagram, which is what this diagram shows. So what is this height of the instructor? The top of the instructor's head, basically, is what we're interested in. And so if we set up the geometry like this, we can say, oh, look at this. We have a nice triangle, so it's just some trig at this point. 34 degrees is there. And so we can say tangent of 34 degrees is opposite over adjacent, so 2 meters over h, height of the instructor. Our height in the instructor is 2 meters over tangent of 34 degrees. And when I do that, I get 2 over tangent 34 thereabouts gives me about 3 meters. 2.97, 3 meters up. So that's the location of the new height. So this is about 3 meters high. And then we can do the same thing. We'll just redraw the diver picture. So that's part A, the height of the instructor's head. Now the apparent depth of the diver. We're going to expect it to be not quite as deep as 2 meters. So we'll redraw this again. So now we can look to find out the distance that the diver is below the surface. So we'll use this drawing for the instructor looking down at an angle of 34 degrees coming into the normal. And so the instructor sees the diver along the straight line, right? And so that gives us, ooh, this is not a good drawing. If that's coming in at 34, then this is coming in at 34 degrees here. And so the diver, the apparent location of the diver, so here's where the diver image, if you like, sits for the instructor. That's this location. Whoops. This HD. Now, in order to find that, we need to know how far, just like we did before, we need this x distance here, because if we know the distance that the diver actually is in relation to where this light ray comes in, so that's going to be sort of this distance right here, x, then we can figure out the geometry here. So I'm going to redraw again this setup. So I've got this, because I want to know where the diver is located. So we know the diver's angle is 25 degrees, and the diver is 2 meters down, and that will give me the geometry to find that x. So if I do that, I've got that tangent of 25 degrees opposite over adjacent over 2 meters gives me an x. If I look at this, this is 0.93 meters. Okay, so that gives me my x of 0.93 meters, this distance here. Okay, and so from that, I can finally find out where the diver image is by saying, hey, I've got an x of 0.93, and I need to know the height of the diver as seen by the instructor. Okay, so this distance right here that I've labeled h sub d. So if I do that, I'll use my 0.93 that I already found, and I'll say, looking at this geometry again, I have tangent of 34 degrees. I just keep reusing the trig. Is opposite, that would be this, x, which would be 0.93 meters, all over this HD, which is what I wanted to find out. The height or the depth of the diver is 0.93 meters over tangent of 34 degrees, which is 1.4 meters. So we put all of this together, And what we get is this image that's kind of messy here. I'm going to get rid of the things we don't need. We say that the diver is actually 2 meters down, but from the point of view of the instructor, the diver looks like, see, this isn't to scale at all, 1.4 meters. And from the point of view of the diver, the instructor, we didn't actually figure out the height of the instructor, could have, but the instructor is actually 3 meters approximately up in the air from the diver's perception. So when you're in the water looking out, things are going to look like they're higher up, and when you're out of the water looking in, things look shallower than they are. And finally, we can look at refraction to look at total internal reflection and finding the critical angle associated with things. So if you have one material like water, 1.33 index of refraction of water, and then there is a layer of ice floating on the water, for example. So the index of refraction of ice would be 1.309 if it's not too cloudy. It depends on how it nucleates as to what kind of index of refraction we get. Then there's a point at which we have the index of refraction is such that we can have internal reflection. In other words, we can have light that's from beneath the water. For right now, we'll talk about that. And it comes up like this, and it just barely skates like that. That is our critical angle. This is the critical angle. Because if we go at any higher angle like this, then the light is going to reflect. Okay? That's the way the critical angle works. And so we have, light that comes like that. So that's telling us the critical angle is that in this case of the water, sine of critical angle, this of the water in this case, is equal to the index of refraction of the next material, index of refraction of ice, sine now of 90 degrees, because that's where we are. So that way, if we get a bigger angle, we'd be asking for, I don't know, negative value. It wouldn't work. Our calculator would say, hey, that's too big to get the sine of that angle. That's another way you know you've got reflection. So if we put these numbers in, we just have 1.333 sine of this critical angle is equal to 1.309 times 1. And so sine of the critical angle is 1.309 divided by 1.333 equals 0.982, and so if we take the arc sine of that, that gives us a critical angle of 79 degrees. So I didn't really draw this to scale. It would be almost, it would be much closer to something that looks like this. Okay, and that's because these indices of refraction are really close. When the indices of refraction are a little more different, then you end up with this critical angle closer to 50 degrees, 48 degrees when you're talking about water and air.